So I'll put the assignment I have made it. I'm just verifying a couple of things. So probably by later this afternoon, the assignment should be uploaded. Assignment will be due in about 10 days from now. Okay, 10-12 days from now. Okay. Several of you had felt that the classes are going slow. Several of you have felt that the classes are going too fast. But really, what is the thing is whether or not you are reasonably able to answer the questions that are there in the assignment. Okay, that's really the aim for it. A lot of times when we think that we have understood the concepts very well, but when it comes to actual problems, we realize that there are certain gaps in understanding. Sometimes we actually think that we have not understood anything, but really when we look at the problems, we actually realize that okay, it's actually fine. It's not as bad as what I thought. Okay. Again, the lecture notes are available. So therefore, when you take down the notes in your notebook, you don't have to really copy things down the way you used to do in a blackboard and chalk type of a setting, because all of these notes will be available to you. What you need to focus on is basically summarize based on what you have understood. Okay, so the break that you get after the end of 3 or 4 classes, you're probably doing not more than 4 classes, I hope. Maybe some of you might be doing 5 classes, but 5 classes I think. Yeah, don't do more classes than that. What you need is basically some time to assimilate the things that you have learned. Okay, that assimilation process is very important, because when we sleep, there's a lot of processes. I've talked about it once. A lot of processes that take place when we are asleep, which take the material from our RAM and puts it in our hard drive. Okay, and again when it puts it in the hard drive, it's puts it under different categories in hard drive. Something that is going to be useful in the immediate future, something that's not going to be useful. Things that is not going to be useful will kind of get eliminated from your hard drive as well, or overwritten in your hard drive as well. Things that are there in your RAM are quite likely to get overwritten within a few days time. So something that has been discussed today, try to revise it within say 48 hours or so. That will help reinforce the things. Again, you would have seen that you have revised things only before the exam, and you have not necessarily forgotten everything. So it's not yes and no, and so these are basically strategies that people adopt, and in order to do the learning in a more reinforced manner. We utilize the hardwired structures that our own brains provide in order to learn in a better manner. Okay, so that's going to be my very strong recommendation to you. Second is, don't rely on memory. Most of the exams that I will have in this course, as well as I'll probably teach you a programming course. I'll also be doing a programming course next semester. As much as possible, I don't want you to rely on memory, in the sense you don't need to mug up formulas. You can. You don't need to mug up formulas, but it doesn't mean no rely on memory. It means you don't need to remember anything. Things that you do again and again, by nature, you'll remember. What's the atomic weight of hydrogen? 1, 2 approximately, right? You didn't mug it up now. When you are 10 years old, you mugged it, but now, because you have used it so many times, it's something that you remember. Okay, some people said 1, some people said 2. Atomic weight, molecular weight, the difference, right? So that's why I say that, yeah, you would remember things, but don't rely on memory, especially in your research, because is it 1, is it 2? It's better to not rely on memory, but quickly look up, for example, Perry's handbook, to see whether or not it is 1 or 2. Okay, I do that even for reasonably simple things that I have not looked at, for a few weeks. I will not rely on memory. Even though I have been in this profession for more than 2 decades, I try not to rely on memory. Okay, so okay, so just a few things that I have found useful. Okay, so terminologies, just a quick recap. Concentration, we are going to use C. Concentration is in terms of moles per liter, moles per meter cube, moles per centimeter cube, moles per ml, and so on. The total concentration is thus just the sum of concentration of all species. Okay, mole fraction is a fraction of concentration divided by total concentration. So if you sum that up, summation of x is going to be equal to 1. Okay, so that's where you get this from. Likewise with partial pressure as well. Okay, the place where you get, or you have said is confusing, is the rate of reaction Rj. Okay, if you have written AA plus BB given CC plus DD, okay, then Rj is the rate okay. Again, it can be moles, kilomoles, it can be cc, liters, meter cube, it can be minutes, seconds, hours, but it's number of moles per unit volume per unit time. That's what the rate is given as the reaction is written. Okay, this is not the definition, this is a shortcut. Okay, definitions can potentially get a little bit more complex than that, but if you follow this shortcut, you will reliably not make mistakes for 99.9% of the cases. Okay. Now, how is this related to minus Ra? If this was rewritten as okay, then your minus Ra is just Rj. Why? Because the stoichiometric coefficient is minus 1. Okay. Again, this I am saying because there was a question, not by one student but by multiple students. I am not going to use the Ra terminology simply because it is going to be confusing. If you find it more convenient to use, there is nothing wrong in using it. Okay, just remember the context in which it was used and it should be perfectly fine. Okay, don't rely only on the final formulae, also understand what were the assumptions that had gone in and how the formula was derived. Okay, and quickly check in the problem statement whether or not the assumptions were met, and that's sufficient. Okay. Something that will happen all the time, especially in your research but also in this course, is I will provide you in problem statements information that need not be necessary to solve a particular problem. Okay. In your undergraduate, you have always been used to, if like Shakespeare's plays, so Shakespeare had made a comment that if you introduce anything in Act 1, you need to definitely use it by Act 3. Okay, that was Shakespeare's statement. So basically, if in a play, if you introduce something, you need to use it, otherwise don't introduce. That's not how research works, that's not how life works. Okay, you might sometimes have much lesser information than is needed to solve a problem. Sometimes you have more information that is needed to solve the problem. You need to figure out that some of the information given to you is extra. It's not necessary to solve the problem. Okay, so there would be a couple of questions which otherwise are very simple 20-second questions, but all I will do is by adding one more information, I can change it, change the way. This is again an example from, this was really my first year when I taught a course. I gave a particular problem, and then a simple problem, and I think pretty much 49 out of 50 students or 48 out of 50 students were able to solve it. So next year when I taught that same course, I thought, okay, I'll just give that same problem, but with that problem had come from my postdoc experience. So I'll give the backstory that I have seen in the postdoc. So I gave that backstory, which fortunately in my view now looking back contained one more additional information that was not required to solve that problem. Otherwise the problem was very similar, and only 25 students solved it. Okay, then the next year I thought, okay, let me make this problem a little bit tougher. Instead of giving this problem for 1 mark, the exact same problem I gave for 5 marks. Guess how many out of 50 students got it? 2 students. And in the exam, both of them had big smile on their faces. One of them called me to ask. I said, yes, your answer is right. I know exactly why you are calling me. If it's a 5-mark problem and you solve it in 10 seconds, so be it. It's not necessarily a trick question. It's, I mean, that's how it might be. Sometimes it, you know, for example, in our research, there's something that we have done, you know, at 1.5 years, 2 years, I have struggled in order to figure out the solution, and we have published a paper, and literally it has 1 citation, which is just me citing my own paper, and there was something else that, you know, worked very well. Pretty much, you know, I started working on it. 3 months later, I had the first draft of paper. This was during my postdoc, towards the end of my postdoc. So, you know, hard work of 7 years prior to that was the reason why I could do that so quickly. You know, but literally 3 months, and like, oh, nobody is going to read that paper. It has more than 100 citations. Okay, so it's not about how easy or difficult the problem is. It's about how relevant the problem is to the current situation, and the relevance is a function of time and location. Okay, so please remember that. Again, all of you are postgraduate students, whether you are interested in job or whether you are interested in research or both, this is applicable universally. Okay, it's not about what you have done. You will get maximum appreciation when it's projected from the perspective of the person who is receiving it. So if he or she needs something and you have done to address that need, that gets maximum reception. When it comes to industry, it's called a push or a pull project. Pull project is something that a customer requires. Push project is something that you have a solution for. After speaking to a few people, you realize that, oh, this is a problem that you will be able to solve. So you solve it because it's a problem that you can solve, not because it's a problem that the customer needs to be solved. The former ones are the ones that that see success faster. The latter ones are the ones which either don't see any success, which is 95% of the cases, or in the remaining 5% of the cases which change the field quite significantly. Case in point, iPhone, right? There was no need for iPhone when iPhone came about, or iPod. I'm from that generation. Which, how many of you know iPods? Okay, a few. So iPod was the original iPhone. It had nothing, but the only thing it could do was play music, and literally there was just one dial and one play button. There was nothing else. Okay, then you know, the next generation iPod with touch screens and other things came up, and then the iPhone came. There was absolutely zero need for iPhone in the market. Nobody was asking for iPhone in the market, but that has completely revolutionized everything. Whether it's fortunate or, from my perspective, unfortunate consequence of that revolution, I don't know. But anyway, it's here to stay. Okay, so that's the difference between push and pull projects. Okay, I figure out innovative ways to waste time. So anyway, okay, so Going forward with a bit more recap, the derivations that we had, we chose a control volume, and we did the analysis of any extensive quantity that is conserved. Okay, which would be moles, total mass, moles, energy, momentum, typically for chemical engineers. There are other things also, electrical engineers would have electric charge and so on also coming into the picture. Okay. So, that is what we are going to use a little bit in today's lecture. So, that was a quick recap. Something that is coming up. Oh, well, someone asked, give me examples. So, let us say we have water gas shift reaction. Okay. Where is water gas shift reaction useful is when you generate hydrogen, let us say from steam reforming type of reactions, you get carbon dioxide, carbon monoxide and hydrogen. You want even more hydrogen and you do not want to emit carbon monoxide. So, what you do is you carry out a water gas shift reaction, and again you might have studied high temperature shift, low temperature shift, because it is carried out in two stages. Why? Because at higher temperatures the reactions are favored kinetically, but because it is an exothermic reversible reaction, so at lower temperatures the reaction is favored thermodynamically. Okay. So, we are talking about reversible reactions. And you have really learnt in CRE thermodynamics in the context of reversible reactions. In chemical kinetics in chemistry, you have learnt thermodynamics in the context of reversible reactions, and when it comes to kinetics, Arrhenius law. Okay. So, now the rate expression is going to be some function of temperature and concentration. Okay. It could be temperature and concentration, it could be temperature and partial pressures, it could be temperature and number of moles, but typically it is temperature and concentration is the rate. R forward, I will say, is a function of that. Okay. And typically if it is a reversible reaction, then there will be equilibrium. Okay. And this ratio, the ratio of concentrations to the power their stoichiometric coefficients. Okay. Products stoichiometric coefficients are positive, reactants stoichiometric coefficients are negative. This is known as Kc, or equilibrium constant, that is concentration based. Okay. How we get that, how we use that is something that we will start talking about from the next class onwards. Okay. Now, the other thing that you would have learned in thermodynamics is your K equilibrium is related to delta G naught of reaction, Okay. So, what that is, how to use it and all that, we will come to that in the next lecture. We will revise those concepts in the next lecture. Okay. But this is to really complete everything that we are talking about. Okay. So, the temperature dependence based on Arrhenius is an exponential dependence. Okay. And if you see the nature of this and the nature of this, it is similar, not the same. Okay. And how does this come out from thermodynamics and so on, or from chemistry aspects, is something that we will talk about in the next lecture. Okay. Oh, yeah. Which one? Yield formula. Yield, okay, so the question is, in the formula of yield, what's the denominator? Okay, a general answer is we'll have to treat it on a case by case basis. Okay, we need more information to define things like yield, selectivity, and conversion. Okay, what I mean by that is, if we have a situation like this, the answer is relatively straightforward. Okay, why? Because you have, your aim is to generate as much as H2 by pretty much by consuming H2O. So, H2O is direct consequence, sorry, H2 is a direct consequence of the reaction from H2. So, the yield in this reaction of H2O. So, the yield in this case will be based on molar flow rate of hydrogen out divided by molar flow rate of H2O in. Okay. But this is from research of one of my students. She is looking at an oxidative dehydrogenation reactions using CO2 as an oxidant. This is the desired reaction. Okay. The undesired reaction three carbons, 2 oxygen, 4, 5, 6 hydrogen. I think it is balanced, but if it's not balanced, we can balance it. Okay. Now, in this reaction, carbon monoxide comes only from C2H6, sorry, CO2. But from in this reaction, carbon monoxide can come from CH2, sorry, CO2 as well as C2H6. Now, this is how to define yield is very complex. Okay. In research, some authors will define what is called as carbon yield. Okay. They will define what is coming in is flow rate of CO2 plus 2 times flow rate of C2H6. That is the molar flow rate of carbon coming in. Molar flow rate of carbon going out is 2 times C2H4 plus 1 times CH4 plus 1 times CO. Okay, so the yield of C2H4 would be 2 times C2H4 divided by the sum of everything, in which case the maximum yield of C2H4 that you can get is 2 by 3, 0.67. Some authors will say that is a ridiculous definition, because if the reaction works perfectly, the yield should be equal to 1. So, we will define it as flow rate of C2H4 out divided by flow rate of C2H6 in. But then if the parallel reaction is taking place, okay, then it starts getting very complicated how you analyze this reaction. Okay. This is something truly beyond the scope of this course. The reason why I am giving this example is to show you a very live example of why it is important for us to define terminologies very clearly. Okay. Different researchers in their papers will define these terminologies and will define it differently, and based on that you cannot just say the analysis, oh these guys had a yield of 60% and these guys had a yield of 90%, so this was better than this. You cannot say that, because these guys might have defined this as a carbon yield, these guys might have defined it as a C2 species yield. Okay. So the immediate answer to your question is that it depends on the context and it will be defined based on what the focus of your research is. For us, the focus of research is the conversion of C2H6 and carbon dioxide. So we will define the yield really, and the second reaction is definitely an undesired reaction. So we will define the yield based on the C2 species. But for another research group where utilization of CO2 is the key and not C2H6, they will define it based on carbon yield. So the things can be more complex. Okay, as far as this course is concerned, it is going to be based on the focus of the primary reactant that is given to you in the problem formulation itself. Okay, and I will continue doing this whether you like it or not. I will continue doing this. I will give the answer in two ways. One is with respect to this course or with respect to things that will help you avoid confusion, but I will also give you broader context based on my industry and our research experience to actually tell you that some of the things that we have taught you all your life as, oh this is very straightforward, there can be a little bit more nuances in those things. Okay, it might seem boring, it might seem relevant, but yeah, I mean that is one thing that you'd probably have to bear, because well this is a postgraduate course. Okay, any other questions? Okay, so in reaction engineering and in transport, we are interested in modeling of flow systems. Okay, largely that's where chemical engineering departs from chemistry. The focus is on those conversions. For us, the focus is on taking it to large scale. Okay, so when we want to take it to large scale, things are very efficient when we go to flow systems, just the way things are efficient in car manufacturing when you put the car on a conveyor belt. Okay, so when we are talking about flow systems, we are talking about two types of mathematical expressions. Okay, the balance equations, that is something that we have been doing all the time in the last 6 lectures including this one, and then the constitutive relationships. Okay, example of constitutive relationship, physical properties of fluid. For example, liquids density is constant, okay, or for gases PV equal to nRT. Okay, diffusivity, thermal conductivity and viscosity, how they are defined and how they are used are governed by fixed Fourier's and Newton's law respectively. Okay, and then the other thing is the reaction rate equations. Those are also constitutive relations, power law, Langmuir-Hinshelwood, so on and so forth. Okay, the balance equations, which we have been talking about multiple times, mass balance, species balance, momentum balance and energy balance. We have not dealt with the last two at all so far. Okay, this is something that image from 4 lectures earlier. Okay, any conserved quantity, okay, there would be an extensive variant of it, the intensive variant of it. The intensive variant would be, for example, density for mass balance, concentration for species balance, rho u for the momentum balance, and specific enthalpy for energy balance. The extensive variables are mass, total number of moles, you know, momentum we will leave it for now. Energy is the total enthalpy. Okay, so we will define our phi, okay, per unit mass or per unit volume. If it is per unit mass, you multiply it by rho and then you multiply it by dV. You don't need to write this down. We are not going to be held responsible for derivations of today's lecture. Okay. If it is per unit volume, there won't be rho over there, it will just be phi dV. Okay. Rate in is, let us say, a vector f covers all the things that all the ways in which things can move into this control volume. Okay. Okay, that would involve convective and a diffusive term. Okay. Now, what does convective versus diffusive mean? Okay, so I will give you an analogy. Just think of a very long bus. Okay, in the bus you put first standard kids and you put 10th standard kids. Okay, and assume that first standard and 10th standard kids are going for a picnic. I don't know why you have put first and 10th standard kids together, but you know, just for argument's sake, we have put that first standard and 10th standard kids together. Okay, this 10th standard kids, let's assume for argument's sake, are fairly mature, so they will sit in their place or move around a little bit. First standard kids are very excited and they are running around in the bus all the time. Okay, small molecules have higher diffusivity, large molecules have lower diffusivity. Now, you can always argue that the 10th standard kids are more naughty and they would move around, but yeah, that is, if they are more naughty, they are heated a little bit more, so at higher temperatures they move around a little bit more, so we can use that analogy. Okay, so let us say blue kids are first standard kids, red kids are 10th standard kids. Okay, blue kids are moving around a lot, red kids are not moving around too much. Okay, you are an external observer and that bus is moving in front of you. Okay, and think about a film that is in front of your eyes. Okay, that film is the boundary of the control volume. Now you are trying to see how many kids are coming in and out of the control volume. Okay, so the number of kids passing through this fictitious film is the flux. Okay, there is a flux because that bus is moving, there is a flux because the kids are moving within that bus. Okay, the bus is not the control volume. Okay, the control volume is starts or ends at that fictitious thing that you have drawn. Okay, now if the bus moves through that control volume, that net motion of blue and red because of that bus moving is the convective part. Okay, how much do the red and blue convect? They convect in exactly the same way, because the velocity of the bus is what determines how they are convecting. Okay, now if the bus is moving like this, then velocity of bus is equal to what is convecting through that film. If the bus was going in this direction, think about it, the bus might be going, and let us say this is 45 degrees angle. Okay, the bus might be going at a speed of v, but the rate at which things are going through this particular guy is v multiplied by cos 45, right. This is the direction in which it is going. Okay, so people are placed here, let us say 3 kids are placed over here. How quickly the kids will move through this particular film is going to be determined by the velocity of bus multiplied by the cos of this. Is something that again you have done in your high school. Okay, so that is where the dot product will with n comes into picture. Okay, plus you will have those first standard kids, blue kids moving in and out much faster than the red kids. Why? because those blue kids are diffusing faster than the red kids. That part which is captured by the net motion of the bus is captured by rho u phi. The part that is captured because how quickly they are moving here and there is captured by j. Okay. Same thing with respect to energy transport. Energy transport, these kids, you imagine them as phonons. Phonons are something that take the energy with them, and same idea will be there. Just that there are no blue kids and red kids. All of the phonons are of the same type. Okay. This particular picture, if you have ever studied Eulerian versus Lagrangian, this particular picture is the Eulerian picture. Okay, it's based on you sitting outside external frame of reference. Okay, if this is Lagrangian frame of reference, you are sitting on that bus, which basically means that there is only convective that is moving through. Okay, but because of all of these kids moving, okay, now this is where the analogy breaks down. But because of all of these kids moving, the bus will not be a rigid bus, but the bus will expand or shrink. Why it will expand or shrink? Because the bus does not contain the external frame, but bus is basically just sum total of all the kids. Okay, so let's say all of the kids come together and they huddle together because somebody is giving them sweets. Okay, your bus won't be this large square. Your bus will be just around those kids who are there. So now this has shrunk and now this has expanded. That shrinking and expansion is because of the diffusive transport, okay, and that comes in from the Reynolds transport theorem. Okay, you don't have to know any of this, you don't have to remember any of this, but if any time you come across this, for example in your transport course, this is the relationship between Eulerian and Lagrangian. This is how you use Green's theorems and Reynolds transport theorem in order to do the derivation. It's really about where that observer is sitting, whether he or she is sitting in the control volume or whether he or she is sitting externally to the control volume. Okay, the control volume can undergo dilatation. Okay. So, what are the intensive variables? Total mass, the intensive variable based on this definition, rho multiplied by phi, the intensive variable is 1 because intensive variable itself is rho. That is why the intensive variable for total mass is 1. Total species is mass fraction. So, rho multiplied by omega k is the volume based intensive variable. So, this is mass based. Volume based intensive variable is rho k, rho u, rho v square. Okay. So, this is the volume based intensive variable. Okay. What is the diffusive term? The diffusive term is 0 when it comes to total mass because mass is conserved. That is where this idea of equimolar counter diffusion in your mass transfer comes from. Okay. J is 0, where J comes from and so on, I will come to that in module number 8 or 7, module number 7. Okay, we will defer it until that point. Okay, when it comes to momentum, your J, that is the diffusive term, is basically your T or tau, right? And when it comes to energy, basically this is the conductive part and this is the viscous dissipation. Okay, and source term in CRE, this is mostly reaction term, but it is not limited to reaction term. Okay, in species it is this guy, in momentum it is the gravity, and in energy it is basically everything else that is not incorporated. Okay. When we talk about internal energy and enthalpy, there is no generation or disappearance of internal energy and enthalpy. All of the energy balances that you have, you remember where delta H reaction term comes in, those are all on specific, all on sensible heats, okay, not heats of formation. Okay. You didn't understand the last part, don't worry about it. Okay. So, when we do the overall derivation, we will get the overall expression in this term. You can plug in the values of phi, j and g in order to get the overall expression. Again, I am not going to hold you responsible for derivation. Okay. So, earlier years we used to go over this derivation and then we will have 1 week expands into 2 weeks and there is a whole lot of confusion, and then towards the end I would not be able to really focus on case studies. So, we have done away last year and this year we have done away with the derivation of species balance. Okay. What you are really responsible for is this part of your species balance. Okay. And how you can use this later. Okay. The other, so this is the species balance. I will go back and I will erase this, and notations. The final thing of interest, I will put it in black box. No need to mug it up. If there are questions based on this, I will give you the overall expression. Okay. It is easy to convert from mass fractions into concentration. Okay. And this is Fick's law. Again, Fick's law is something that we have studied in our high school. In high school, we would have studied the Fick's second law is remember, this is just a more general definition of Fick's law. Negative sign, why? Always from higher concentration to lower concentration. Okay, so always in the direction of decreasing concentration. Right. And again, if you can't see why it's positive or negative, concentration over here is higher than this. So, if this is higher than this guy, dC by dz is this minus this divided by this minus this. So, that is a negative value because smaller guy, let us say this is 10, this is 8. So, it is minus 2 divided by delta z. So, it is a negative value. The flux is in this direction. So, the flux is in positive direction. So, the flux is positive, dC by dz is negative. So, therefore, a negative term comes in. Okay. So, this is not really a good way of doing things because you might end up getting confused in more complex situations. So, but yeah, I mean this does work for simplified situations, thinking about it this way. Okay. So, because the flux is in the direction of decreasing concentration, that is the reason why you get a negative term. Okay. Likewise, because the reaction is in terms of decreasing concentration, therefore, you have negative values of stoichiometric coefficient on the reactant side and positive values of stoichiometric coefficient on the product side. Okay. Now, the overall energy balance is really an is internal energy balance, and by definition of enthalpy, okay, you can derive the expression in this form, okay, where H is the partial molar enthalpy. there is no reaction term in this at all, because enthalpy is the overall conserved quantity. Okay, but enthalpy is summation of heat of formation plus sensible heat. Okay, and when you take out the sensible component and you take separately the heat of formation component, you will get this balance. In CRE and in a lot of practical cases, this is the more usable But if you talk to mechanical engineers, for example, if you talk about simulations in combustion type of systems, they will use the enthalpy balance. If you talk to aerospace engineers, they will only use enthalpy balance. They will not use the sensible heat balance, because when you have very high flows, there are something else that happens, which is called compressible flow, and therefore they won't look at the sensible heat balance, but they will look at the enthalpy balance. And again, when you talk about all of these things in a more broader perspective, right, whether those boundaries that we have created in undergraduate so that you can understand, those boundaries don't exist in the real world. Okay, when a rocket is being launched as SHAR, okay, chemists and chemical engineers in ISRO won't say that, oh, this is not my work. No, and if they say this is not my work, that will not be a good situation to be in, right? So there will be chemical engineers and aerospace engineers and mechanical engineers and others also who will all work together. And if you are working in a cross-functional team, you better be aware of how other fields do the work. You may not know how to do it yourself, but be aware of how they do and be aware of the equivalence between the equations that you use and the equations that are preferred in those fields. So the equivalence between these two equations, I don't know how to point it out for video, but the equivalence between these two equations is basically through the definition of H, which has the heat of formation and the sensible heat, and you collect all the sensible heat terms and put it on the left hand side. On the right hand side you have the heat of formation term and the diffusive transport term, which is conduction. Okay, and that's what you end up with. Okay, there's one more very interesting thing about this term I just remembered. So when I was working in industry, what we had was, there was a material that was made. There was a material, metal oxide framework based material that was made, but its thermal properties were very poor. So what they did was they added a little bit of graphite to improve the thermal conductivity. Okay, and once the graphite was added, they compressed the material in order to pelletize it. Okay, now if you go to the lab, if you go to my lab, or if you speak to my students and look at, or Arvind's students and look at the compression machine, compression is applied in this direction. It's not applied from all sides, it's applied in this direction. So what would happen is that the graphite would get horizontally aligned. So the thermal conductivity in this direction was larger than the thermal conductivity in this direction. Okay, something that you have not, I'm assuming, encountered ever so far, right? Now the beauty of this term is you can use anisotropic conductivity, which means your thermal conductivity can be different in x, y and z direction. Your delta T is also in x, y and z direction. So your lambda delta T is a tensor, and then you are dot producting it with delta. Okay, fun thing. But yes, so the innocuous looking expression that you thought about all the time can do a lot more than the situations that we had encountered. That was the first time in my life that I had encountered an anisotropic thermal conductivity, but the thermal conductivity need not be the same in all directions. Okay, so that leads me to the end of this lecture. This lecture was intentionally too short. We are not going to go into the derivation. What I will do is also upload a Word document that contains all of these expressions. We are going to use these expressions at various points in this course. We are not going to derive these expressions, but we are going to use them. So, you be aware of the various terms in this expressions, and if needed I can have one additional class where I go over all of these expressions if that confusion is there. Okay. Other than that, there was nothing major in today's lecture. Okay. What I will not go over is basically how do these expressions result in the derivations of PFR and CSTR, and how you can use it in doing the derivations that you have been doing in your undergraduate. Okay. Until 3 years back, I used to do this in the first 3 weeks of the course, and then non-chemical engineers found it a little bit very steep to really pick up. So, this has been moved to week number 9 of this course. Okay. So, we will do all of these things again, but what I request you to do is whenever you get time, just go over this particular part, the module 1E. Okay, I will, this should be module 1E. Okay, I repeat, you are not yet responsible for all of this, but there are some problems that we will do from now until the next few weeks, which will benefit from you recapping this material. Okay, so chemical engineers recap this material, non-chemical engineers just be aware of this this material, so that whenever some concepts like this are encountered, you will find it easy. Not you won't find it easy, but you will at least have some link, and we will take this up in module number 8, not 7, sorry, module number 8. Okay. All right. So that's the end of this lecture. Thank you.